Utiyama assume about the contortion tensor. Okay. Question mark. This is the end of the exercise. So you have just to be aware of the in the original article. This current which he has is the angular momentum current, which has, of course, three indices, and anti-symmetric in I and J, and which cannot be linked to energy momentum in any direct way. And he makes also a remark in this article that somehow the current has a little bit another position in gravity as it has in Young's theory. I think I just may mention because this is only 5 minutes more, in 3.7, Sakurai, Glashow, and Gell-Mann, and Feynman. Then I can start on Monday with gravitational gauge theory. Because now I want to study the reaction of other people to Utiyama's and Young's work in respect to gravitation. And in the book we cited Sakurai. In fact, he wrote a very famous article on strong interaction, which impressed me as a student already in 1960. Glashow, and Gell-Mann. And Feynman. So I just want to cite 3 people, and I just take our book and read a little bit at the end. It's not a good night story, but a wake-up story, you know. You should. So Sakurai, he has a theory of strong interaction in Annals of Physics, 1960, a beautiful article. I think I read it several times. So the idea of Young-Mills, etc., this is a very profound idea, perhaps the most profound idea in theoretical physics since the invention of the Dirac theory. It essentially states, if we have a conservation law of some internal attribute, there must necessarily exist a vector type interaction corresponding to it in order that the conservation law in question be consistent with the concept of localized fields. And this cannot be expressed in any better way. To put this idea more succinctly, internal symmetry, ergodynamics. And now, at the end of his articles, having discussed weak interactions, we naturally wonder how gravitational interaction fits into our general system. And here he makes a footnote. Many experts seem to regard the remaining part of this section as completely nonsensical. So he discussed it obviously with people. Now I read it. According to the Utrecht experiment, the strength of the coupling of the gravitational field to matter is proportional to the inertial mass, which is essentially the rest energy. Thus, we are led to speculate that there exists a deep connection between energy conservation and the very existence of gravitational coupling. The gravitational field, being the dynamical manifestation of energy, is to be coupled to energy momentum density. Now there is energy associated with the gravitational field itself. This is the idea which also Young-Mills expressed. Hence, the gravitational field can interact with itself in the same way as the T=1 Young-Mills B field with the dynamical manifestation, which is the dynamical manifestation of isospace, can interact with itself. So gravity should couple to energy momentum, and a lot of experts seem to not to believe it. Gell-Mann and Glashow and Gell-Mann, 61. just one sentence. Instead of isotopic rotation, we perform a four-dimensional translation at each point of space. Thus, we have in place of an isotopic index another Lorentz index beta, giving us a tensor field H alpha beta, which is basically the tetrad. And Feynman, in his lectures 62, he says, I just quote the last sentence, thus, gravity is that field which corresponds to a gauge invariance with respect to displacement transformations. And of course, displacement transformations are translations and not Lorentz transformations. And this is what Sakurai said was 1960, what Greshow and Gell-Mann 61, Feynman 62, but already 60 and 61, Sciama and Kibble came up with gauging the Poincaré group, and this is then the subject of my fourth double lecture, where we will study this idea. But I hope I have shown you that without a conserved current and without making up your mind which conserved current you want to investigate, you shouldn't do and you should not develop a gauge theory. If you develop a gauge theory of gravity, we take the recipe of Sakurai and et al. But we know, of course, that in special relativity, translations don't live alone. Translations is just a subgroup of the Poincaré group, and the fundamental group of special relativity is not the translation group. Then we would only have energy momentum in the world, but we have also spin in the world. So we know that we have to look to the Poincaré group. So if we have to look at the translation group and gauge it, willy-nilly we have also to look at the Lorentz group and to gauge it, and then we mesh up with what Utiyama did, Lorentz group and the gravitational field. So somehow, of course, also the Lorentz group is related to the gravitational field. But in order to make this somehow more definite, we have to look at the whole Poincaré group and to gauge the Poincaré group, and then we can hope to find a sensible gauge theory of gravity. Thank you for your patience.
Yeah, question just okay, out there. We will have a lecture next Monday, Friday, and the following Monday.
So three lectures to come. Yes.
Yeah. So sorry if somebody came this Friday, this Monday.
Eureka.
Okay, I'm still available if somebody, there was somebody who wanted to ask me about gravitation the first hour, but
Yeah.